Hi, everyone. My name is Karen Garcia, and I'm currently a developer for the discrete computation team in Wolfram R&D. And today we have a guest speaker for our Wolfram live streams. His name is Matthias Geelhoff, and he is an assistant professor at Chalmers University of Technology, currently working in condensed matter theory. He's a developer of Mathematica that made the group theory package called GTPack. He's an author of the book Group Theory in Solid State Physics and Photonics, Problem Solving with Mathematica. He was a postdoctoral researcher at the Nordic Institute for Theoretical Physics in Stockholm, in Sweden. And he completed his undergraduate and postgraduate studies at the Martin Luther University in Germany, specializing in theoretical and computational physics. Matthias also did his PhD in connection with the Max Planck Institute of Microstructure Physics in Halle. His main research interests are in condensed matter theory. And today, Matthias is joining us to present on his group theory package. So Matthias, you have the floor.
All right. Thank you, Karen.
Yep.
Let me just share my screen. All right. I thought, since I'm an external speaker, I will start with a couple of slides to just give you a general introduction a bit into our group theory package. So the topic of today is GTPack and symmetry principles in the condensed matter. Before I start with some information about our package and some examples later on, I thought I will give you a, let's say, very general introduction into the topic and why we actually need such a package. And I just want to show you two pictures, basically underlying concepts of symmetry and symmetry breaking are actually two very central aspects of nature. So on the left-hand side, I show you a very, let's say, well-known phenomenon, which is the fish schooling, where you have a huge amount of fish basically aligning in this school. And this is actually a phenomenon where you feel okay, if you look at this picture, everything looks very symmetric. But it's actually a phenomenon of the symmetry breaking, because if you consider the fish, a huge amount of fish, basically before they start to school, then basically the space is anisotropic. The moment that they all start to align, you basically introduce a kind of main symmetry axis along which all of these fish are pointing. And for instance, if you now invert this picture, then you would basically see that inversion is no longer a symmetry of the system. And it's actually that this pretty much the same phenomena can also be studied in the solid state, where a almost similar effect is, for instance, observed in the ferroelectric materials, which have the spontaneous formation of dipole moments. And then on the right-hand side, I show you a picture which is basically, which could be from the high energy or which could be from the condensed matter theory both. And it's a phenomenon of the mass generation in the fermions. It's a phenomenon which has been known for many decades and where there have been Nobel Prizes and so on. But basically, to just very briefly, if you take a look at the picture in the center, then I show you an energy momentum relation, relativistic energy momentum relation, and which is p squared c squared plus m squared c to the 4 square root of that one. So if you have a particle which has no mass, then basically you have a linear crossing of modes. And the moment that basically the particle starts to develop mass, then you will start to see this gap. And this is actually something which can happen if there's a sufficiently large coupling strength between fermions, which is basically schematically plotted here on the right-hand side, where there's the mass is now denoted by this expectation value of some field. And if you, for instance, follow this some some function over this, like some potential profile of this field, then you can see that there's basically a classical solution if you have like a sufficiently large coupling strength, where you get this basically double well potential, and the system wants to undergo this symmetry breaking. And the moment that the particle basically develops a mass, you basically break symmetry. It's like, for instance, the chiral symmetry or something. So these are two very different examples, which basically show you that there's basically always symmetry involved in many of the processes, but also in the main field of research that I'm interested in, which is more in the quantum materials, symmetry plays a very significant role. Actually, the whole idea of the group theory package started with a course on group theory, which was back in the day given by Wolfram R&D, who is like one of the two developers. So it's me and Wolfram who mainly developed this package. And he back then had the idea that even though group theory and solid state physics and photonics is an exciting topic by itself, it's quite often that actually computations which you do as a student are basically quite dull. And then the idea was, can we actually bring in Mathematica as a tool, which was used at the university back then, or still is? Can we use Mathematica to basically support the students in performing some of these computations, and just to, like, understand the concepts? Because in a certain course level, you basically, like, understand how to add and multiply numbers. So then there's like, there are other things which are more important. So Mathematica can take care of this. And that's basically how it started, that we said, like, we could develop a package together with a course. And this was published in our book, and the package was released. And by now you can see that there's actually, like, the number of users of our group theory package is increasing. And also the number of users of GTPack in active research is actually increasing, that we can use GTPack these days actually for actual quantum chemical investigations and so on, which I'm also interested in myself. Just to give a very broad overview of what GTPack is, it's a group theory package, as I mentioned before, which has about 200 new modules. And if we basically separate in two categories, then there's some like basic group and representation theory, where the package actually allows you to install and discuss point and space groups, get some of their properties like classes and cosets. And the whole thing is also developed for the double groups. For instance, for example, if you take into account like the spin. And on the representation theory side, that's basically the link to the actual physical applications, is that we quite often need quite basic informations like character tables or representation matrices, Clebsch-Gordon coefficients, to do quite interesting things. And that's something which is implemented in this package. But then also beyond that, there are actually applications where we implemented a couple of the modules, for instance, on the electronic structure theory and in the context of the tight binding or the crystal field theory. But it's also actually that the development of this group theory package together with actually this Mathematica language also showed us that there's new ways of actually performing electronic structure calculations. So there's this method which we call MSAS. This is the molecular symmetry adapted spin space theory, which I'm basically just mentioning, will be mentioning shortly. But there's also like applications on the photonic side, and the Landau theory, this Landau theory of phase transition, which basically corresponds to this double well potential plot that I showed you before. So right now, this is the last slide before I will start to show you a couple of the examples, how GTPack looks like. Right now, the package is actually hosted on our own webpage, which is gtpack.org. So on this webpage, you can always find the latest version. Some of the content that I'm going to show you today will be available from GTPack 1.4, which we hope to release soon after. But here we also have a forum. You get a couple of the tutorials and documentation, and we are actually working quite actively in trying to increase the amount of tutorials to make GTPack actually more accessible to everyone who wants to use it. Yeah, this is basically the last slide. So let me quickly switch my screen sharing to a example notebook. Which is just a second, which is this one. All right. All right, so this is the, just a second. Yes. So this is the notebook. Let's assume you went to our webpage and downloaded our group theory package and installed it in the standard way as Mathematica packages have been installed until now. So I know that there's a Wolfram is basically constantly improving this functionality of installing packages. So this, we are a bit in this, let's say, previous version where you download something and install it from there. Then you load our group theory package with the needs group theory command. And if I evaluate this one, then it just takes a second, which I can explain in a second, because it installs a couple of
Matthias?
Yes.
Hi, you are not sharing your screen. Do you mind switching to it, to the notebook?
Oh, sure. Is there only, let me see. I thought I was sharing it.
No,
Maybe
I think it's, yeah.
This one. All right, here we go, right?
Right.
Can you see the notebook?
Yes, I can see it. Looks
Right.
good.
I'm sorry.
No, no worries.
Let me start with the loading. So this is there. There's not much done so far, but thanks for the comment. So we load the group theory package with the needs group theory command, and then it will basically show you some information. A second, what's happening right now? So it basically starts to install some symmetry access. So these symmetry access I will show you in a second. They are needed for basically all the symmetry transformations which are included in the package. And then just to basically give you a very rough overview before we start with a couple of basic examples. All the comments that we basically implemented additionally in our GTPack tool, they start with GT. So if I run this GT star, then we basically see everything that has been implemented in the framework of this group theory package. And then you can see that there's a couple of the sub packages which already hint you to what the application of these modules could be. So there's, for instance, an angular momentum package which allows you to install certain matrices for the angular momentum operator, or like representations of the spin groups. We have a couple of the additional comments which we added to the auxiliary package, including, for instance, the work with quaternions. Then we have the basic package, which basically involves all comments about the structure of groups, like calculation of classes, cosets, and so on. We have a crystal field package, which is basically from the applications which I just mentioned. We have some basic handling of crystal structures involved. We have some of these electronic structure tools, packages for installation of groups. There's this new package which will come with GTPack 1.4 about the Landau theory, which right now only has one comment, but which we plan to extend further. And there's a package about representation theory, space groups, symbols, type binding model, vibrations, phonons, and these sort of things. So it's in total, it should be in the order of 200 modules that we get here. All right, so let me start with the first examples, just to get you familiar with the underlying algebra that we have. Actually, in this group theory package, we basically work with predefined symmetry transformations, and these are denoted by this like Schoenflies like symbols. For instance, the C3Z denotes the threefold rotation about the z-axis, and these are like symbols which we basically defined during this installation of the symmetry axis. So Mathematica basically recognizes this as a known object. We also have, for instance, common like symbols involving the inversion, which are basically then reflected to mirrors. But internally, if we want to do calculations, then what we always do is we basically relate to these symbols matrices. And so we have a comment which is get matrix, which actually tells you, okay, what is this object? And for instance, in a representation as a rotation matrix, then GT matrix gives you actually the rotation matrix of C3Z, right? The same holds then, for instance, for the fourfold rotation about the x-axis, or the twofold rotation about the axis alpha, which is actually defined as one of the basically one of the corners of a cube, right? These are symmetry elements which typically show up in crystal structures. But as I said before, GTPack also allows you to work, for instance, with double groups. So we can also represent elements, for instance, in terms of SU2 matrices. And that's quite interesting, actually, because for the SU2 matrices, there's actually two realizations of this C3Z. That's why these things are also called the double groups. There's also a version with a minus sign. So if I, for instance, use GT SU2 matrix, let me see if that one was the right one, then there's also a corresponding double group element, right? Okay, I just get a question about the generators for the monster group. I will show you in a second like how we install point groups. We are actually, so far we don't have any examples on the monster group. I know that the monster group is something widely discussed in the computational algebra community, but most of the, let's say, of the groups that we are interested in are basically like crystallographic groups. But we can install groups, for instance, from generators, right? So for instance, there's a common GT group from generators. And if I put in the C3Z element, then I get the cyclic group containing 3 elements. And then, for instance, we have comments like GT group Q, which asks if this list of symbols is actually a group. So if I evaluate it, then I get true. But we also have a couple of the predefined groups. So for instance, the group above can also be called C3. Note that there's now the difference. There's no Z involved, right? Because this is just a general name for a group, for a crystallographic group. Then we basically get the same group as above. Same common GT install group can also be used to install space groups. These are, for instance, denoted by their space group numbers. So in 3 dimensions, there's 230 space groups. And for instance, one of them is the space group 19. And of course, keep in mind, like space group by itself is an infinite group containing basically all infinite discrete translations of the letters. So what we actually mathematically give here is like a factor group of the space group with the group of the pure translations. Right, but this is a group which is then typically isomorphous to a point group. I mentioned before that we also have capability of installing double groups. This can be done by an internal representation. So if we change the representation of this installation comment, for instance, to SU3, So if you note, for instance, here install group C3C said that the standard representation has changed to O3. So these are basically conventional rotation matrices in three-dimensional space, but we can now change to SU2. Then we get a group with 6 elements where we basically have the double group partner for each of the 3 elements that we had before. And if I now evaluate the comment GTGet matrix, then we will see that the GTGet matrix comment gives you a SU2 matrix, right? Compared, for instance, to the rotation matrix, which you can also get, which is then GTGet rotation matrix, right? So I just see the question about the wallpaper groups. Unfortunately, we don't have the wallpaper groups installed as they are right now, because we have 32 point groups, and if I remember correctly, there's more than 32 wallpaper groups. Let me show you something on the representation theory. So I just want to pick a group which has slightly more structure than C3, which I showed before. So let's, for instance, install the group D4H. This is basically the group of a square, which leaves invariant two-dimensional square. And one of the, let's say, basic quantities that we often need in physics if it comes to representation theory is the character table. And that's a comment which we implemented with. So this character table is basically computed directly here. And you can see that the group D4H has 10 reducible representations. They are now denoted in the typical way chemists like to denote it. As far as I can tell, this is the so-called Mulliken notation. And we see that this character table is square. So there's as many irreducible representations as there are classes. And for the classes, I basically give the like one of the class representatives. And you can see the list of all the classes below. So just to give a basically quick reminder about the representations, basically a representation of a group is a set of matrices which is homomorphous to the group. So it basically maintains some of the structure of the group. And irreducible representations are basically representations which cannot be block diagonalized any further. And the character table basically gives you the traces of all of the representation matrices, because the trace of a matrix is basically transformation invariant. But we also, instead of having just the characters, we can also install an actual matrix representation. So for instance, if we take the representation EG, this is the one here, which is a two-dimensional representation, which you can see from the character of the identity element, which is 2. Because identity element is always represented by an identity matrix, and the trace of a two-dimensional identity matrix is 2. Then we can also install all of these representation matrices for the EG representation, which is a two-dimensional representation. And at the same time, we can, for instance, also pick a one-dimensional representation, for instance, B1G. Right, and then you will see that one-dimensional representation basically contains only one-dimensional matrices, so it contains basically numbers, right? So these are a couple of the, let's say, elementary properties of groups. And now I just want to give you a, let's say, a quick application of this. There's this really interesting quantum phenomenon called superconductivity, which is basically the phenomenon under which material completely loses its resistivity. And what you can see here is basically a magnet hovering over a basically a high temperature superconductor. High temperature means that it's superconducting below liquid nitrogen temperature. And there's a so-called Meissner effect, which says that the superconductor basically expels the magnetic field. And so it's like a perfect diamagnet, and it makes this this magnet basically hover over the superconducting plate. And there's a beautiful theory about the superconductivity, which I don't want to go into here. But there's also like a phenomenological theory on the superconductivity, namely, as in the same way as I showed you before, you can basically write down a like polynomial expansion of a thermodynamic quantity called the free energy in terms of the superconducting order parameter. So typically, if we talk about ordered phases of matter, then we have an order parameter, and the order parameter is the quantity which actually breaks symmetry. A superconductor, for instance, breaks so-called Q1 gauge symmetry. And if I write down, for instance, let's say if I take a superconducting gap, which should transform as a B1G representation of this group, then basically the Landau free energy expansion looks fairly simple. It basically only has two terms up to fourth order, a second order and a fourth order term. For the superconductor, basically the superconducting gap needs to enter as an absolute squared because it might be complex valued, and the free energy is supposed to be real to satisfy the U1 gauge symmetry. So this is this is obtained with the comment GT Landau expansion, but these expansions actually get slightly more evolved if you basically evaluate it on the, like for instance, on a two-dimensional representation. So if you have a like multi-component superconducting order, then you also have terms in this free energy expansion where actually both components of the superconductor couple. And in the past, there have been a couple of remarkable papers, among others, the one by Sigrist and Ueda, which I cite above, which basically give you free energy expansions of all sorts of symmetry groups which are relevant. But actually, like with GTPack, you can now algorithmically just calculate it, and you can basically expand this Landau expansion even further. So you could add additional degrees of freedom, even if they are not superconducting. You can, for instance, ask the question like, can a two-component superconductor couple to a material magnetization or polarization and so on? And then the system basically writes down for you the symmetry allowed terms of this expansion. I just want to mention at this point, because I felt it relates a bit here, that there's like further methodology in the representation theory package. So for instance, we can calculate a product basis, right? So if we, for instance, consider we have a superconducting state with the basis eta1, eta2, and a two-dimensional representation, I can ask the question like, what is a potential basis of the direct product of EG star cross EG? So that means I can in principle construct 4 terms by brute force, because now it's like a 4-dimensional space. But I can also ask, like, can I diagonalize this space in terms of the irreducible representations of the group? So for instance, if we take now the squared of all the characters of the EG representation, is then this list, right? Like if I just remind you, the characters of the representation EG looked like this before. So it is very 2-dimensional representation. Then I can use a comment which is called GTIREP, which actually gives you the decomposition of this direct product in terms of irreducible representations of D4H. And now I can, for instance, say I want to focus on B1G, and I want to construct a basis in terms of these functions, which is basically invariant, or which transforms as the B1G representation. And this is typically done in terms of the Clebsch-Gordon coefficients, where I take into account this product representation and then my representation B1G. So I get a list of Clebsch-Gordon coefficients, and out of these Clebsch-Gordon coefficients, I can now basically construct my symmetry adapted basis, which looks like this. And there's actually a quite nice application to this, which I don't want to go into even further, but with these tools available, it actually becomes very easy to evaluate. There's been a quite interesting recent review article by Fernandes, Schmalian, and others on the vestigial order of superconducting states, which where they basically explain that it can happen that if you are basically in temperature slightly above a certain superconducting transition, then you can already see in some cases some other order phase emerging before, and these are actually such products of various states. These are so-called composite orders. So this is basically a combination of two order parameters. And with these like Clebsch-Gordon coefficients and so on, one can now very nicely construct like how these order parameters would behave. And one can even write down the effective Landau theory for these bilinears, actually. Now I slightly want to switch gears from the applications in the condensed matter, from the superconductivity to the quantum chemistry. And there's a well-known theory which is called the crystal field theory, which has been around for, yeah, I would say almost 100 years, considering the first paper by Bethe as the initiation of this field. What it basically says that is like, consider you have an electron in some atomic orbital, and the atom typically has the like spherical symmetry. So it's now not the symmetry of the orbital, it's like the symmetry of the system, which is spherical. And if you have a spherical symmetry and you have no spin orbit coupling, then you will see that you have that you're allowed to have a 5-fold degenerate state for the d electrons. There's a 3-fold degenerate state for the p electrons, 1-fold degenerate state for the s electrons. And like following this logic, you can basically build up all of the periodic table. But if you start to lower the symmetry from spherical symmetry to something else, like for instance to the octahedral symmetry, then you will see that this state is no longer degenerate, but it will split. Right? It will split in two representations called E and T2. And if you decrease the symmetry even further, for instance, from an octahedron, you start to squeeze it, for instance, then you get a square symmetry, then these states might split again even further. And it's a very important theory because it, on the one hand, it describes like impurities in crystals. On the other hand, it's a very powerful theory to describe Legend fields and complex chemistry, but also like, for instance, metallic atoms in metal organic molecules. And with GTPack, like we have different options to deal with such system. One is basically to just describe first the splitting phenomenologically. So here, for instance, we want to install this cubic group, which is called OH. It's a bit bigger group, so it just takes a second. So again, this group actually has 10 irreducible representations, which you can see here. 4 of them are 3-dimensional, 2 are 2-dimensional, 4 of them are 1-dimensional. Classes are given below. And now we want to see like if we can say anything about this splitting from D to E and T2, then what we can actually do is we can basically install the characters of the spherical symmetry, so which we call basically the angular momentum characters, which are basically characters of the group SO3 or even SU2. It's like a more generalized comment, but for the integers, it gives you basically characters of SO3. So if we perform this comment, then it gives you the characters per class. So as you see here, we have 10 classes, so it gives you a list with 10 numbers concerning to the characters of each class in this representation. And as we know that the d orbital is 5-fold degenerate, we can also see here that this representation is 5-dimensional actually. So the dimension of the representation always corresponds basically to the degeneracy of the electronic states. And now if we take this representation and we decompose it in terms of the irreducible representations of OH, then we can see what we had before. We get this two-dimensional representation, e.g. and a three-dimensional representation T2G. And if we repeat the same thing actually for the square symmetry, calculating the classes for the square symmetry, then we get the splitting into four representations. Three of them are one-dimensional, one is two-dimensional, so it adds up again to be 5, right? But now we can also ask, like, okay, what is the relationship between OH and D4H? So D4H is actually a subgroup of OH. Then we can actually use this common GT crystal field splitting, which now gives you the splitting of the representations of the group OH in terms of representations of D4H. And here we can see, for instance, that T2G splits into B2G and EG. So these are two of the representations emerging here. And that EG splits into A1G and B1G. These are the other two. So everything is consistent. Right. Just briefly want to mention that there's also like quantitative ways of performing the crystal field theory, which we started to implement in GTPack. So there's, for instance, the option of expanding or of representing the electrostatic crystal field around the central atom. So imagine you have like a, for instance, metallic atom inside a metal organic molecule. Then around this atom you have some like organic parts, organic molecules, and these molecules basically interact with the central atom in terms of electrostatic interactions, and I can expand this electrostatic interaction basically in terms of spherical harmonics, or I can expand it in terms of operator equivalence or something. And this symmetry adapted expansion can basically be obtained using GT crystal field. So now you see a couple of parameters here. There's an expectation value, or radial expectation value. There's a crystal field parameter, A4. And there's these functions Y, which are basically the spherical harmonics. Right. And now if we want to evaluate this, then we can also replace the spherical harmonics by operator equivalence. So there's, for instance, this so-called Buckmaster-Smith-Thornley operator equivalence. So this one we can, for instance, evaluate for this element here. If we have Y4, 0, then we have this element 4, 0. And then we want to evaluate everything for the total angular momentum of 2 corresponding to our d electrons. So we get again a 5-dimensional matrix. And if I just plug in some numerical numbers for the other parameters without caring about it too much, then you will see that again, for the OH symmetry, you get 5 eigenvalues. 2 of them are twofold degenerate, and 3 of them are threefold degenerate, right? Which again reflects the G and T2G symmetry that we were obtaining basically qualitatively before. There's also ways of making this quantitative, which I don't want to go into too much. At some point, we started to implement let's say, internal database system, so you can bring in your own data files for certain central atoms, for instance, which you're always interested in, so that you don't need to do everything by hand. Again, there's, for instance, a comment which is called crystal field database info. There's also a set of data sets which is a bit hidden in the documentation of GTPack, but which we also provide. There's, for instance, this database here contains calculated radial expectation values of various lanthanides, which we have calculated using the density functional theory a while ago by Forstreuter and others, which basically contains the parameters that we need. And if I now, for instance, let's say, want to have parameters for holmium, then I can use this database retrieve, and then I get the replacement rules for these constants as they might emerge in the crystal field expansion. Note that this one is now a bit more general, right? Like in the cubic or octahedral symmetry, we don't have an R2 contribution, and we didn't expand until 6th order, which we also shouldn't have for this example. There's also like a comment on the evaluation of crystal field parameters themselves. these are these parameters A, which we had here above, right, which I picked numerically. If you have like a list of like molecular, like atomic positions of this molecular field and charges, then you can basically evaluate these parameters using a so-called point charge model, saying that like each atom is basically just a point charge. But I also want to briefly outline what I mentioned before. There's a recent work which we did together with Jeffrey Reinhardt at UCSD, that where we basically discussed like how one can generalize crystal field theory, because crystal field theory in all its beauty and accuracy also has a couple of difficulties, among others, if it comes to discuss systems where many angular momentum multiplets are very close in energy, or if you want to discuss systems with loss, if you want to say like, okay, is there like a non-Hermitian Hamiltonian which corresponds to a certain central atom, for instance, in the presence of molecular vibrations or something. But I want to show you like a very basically the same example again, where you don't see the obvious difference to conventional crystal field theory other than the construction itself. So we start by, like before, we basically only calculated characters of this angular momentum representation, but now we can also calculate specific matrices. This is done by angular momentum representation. So for instance, then all these representation matrices look like this. These are now the basically representations of O3 for the for L equal to 2. And now we can basically generate a matrix, like which we say should be our Hamiltonian at the end. So I just use a 5x5 Hamiltonian, which should describe my d electrons in some cubic field or octahedral field. So in general, this is just a 5x5 matrix with unknown coefficients. But if we want to see what of this part is actually invariant under symmetry, we can now apply basically a so-called projection operator based on these representation matrices acting on this matrix. And if we do that and solve basically, so we say that this projected Hamiltonian should have the same form as our initial Hamiltonian. So that basically tells us that some of these parameters in the initial Hamiltonian should be 0, right? So we can solve for that using Mathematica's own solve comment. Here I also embedded something on the hermiticity, which we actually don't need. So if I just bring in the solutions of this solve comment, then I get a Hamiltonian matrix, which is diagonal. And again, if I look at this diagonal matrix, like diagonalizing a diagonal matrix is quite simple. So we basically know exactly what the eigenvalues are. And if I look at the eigenvalues, then I see again, there's a 2-fold degenerate eigenvalue and there's a 3-fold degenerate eigenvalue. So this is again a third case, basically confirming the same thing. So if you are interested in this method, I'll just give you the reference up here again. It's on can be found on the archive. Last but not least, it's now 45. So maybe I will just briefly mention a final example in 5 minutes. This concerns the like tight binding method, like constructing electronic structures of periodic solids. So then you get basically electronic bands. And one of the, let's say, textbook examples for tight binding calculations these days is graphene, which is a 2-dimensional version of crystalline carbon, and has the crystal structure shown here, which we actually get by putting in the crystal structure information. So these are basically the name. Okay, here we called it just C honeycomb, which basically corresponds to the structure. It could also be graphene. There's some information about the different names of the space group. There's the lattice vectors. Here you can see that it's 2-dimensional, so the third vector is just 0. And then there's like 2 atoms in the unit cell, which are, I don't know if you can see it now. There's a blue and the orange atom. So if I construct, like if I focus on one of these periodic patterns, then I see that it's always this combination of the two atoms which repeats, right? If I walk along these lattice vectors. And to construct the tight binding method, this is probably now something which only makes sense to you if you heard about this method before. Then you basically need to you need to have some sort of knowledge about what is going on around the central atom. So you basically expand. You basically consider the hopping to certain neighboring shells, hopping of electrons, for instance, to its nearest neighbors, hopping of electrons to its second nearest neighbors, and so on. So for that, we have comments to actually produce these shells. So we can generate a cluster of atoms using the GT cluster. We can distribute this cluster into shells using the GT shells comment, which basically then tells us that there's, for instance, a certain type of, there's a certain amount of atoms at like a distance 1. There's 3 atoms, so these are the nearest neighbors, right? These are those ones, 1, 2, 3. At a distance square root over 3, there's 6 neighbors, 1, 2, 3, 4, 5, 6. And we could play this game even further. But for instance, if we focus only on this, like, let's say, nearest neighbor version, and we can construct a Hamiltonian, for instance, involving the s and p electrons of the carbon atoms. This is just a plot telling you which entries of this Hamiltonian are non-zero. But now if you take a closer look at the pz orbitals, so if you remember your chemistry classes, then you might remember that there are 3 p orbitals. One of them are basically along the x, and one is along the y, and one is along the z direction. And now if we consider this 2-dimensional object, then we can say that, okay, something interesting has to happen for the x and y electrons, and something different has to happen for the pz electrons, because they are basically sticking out of plane. And if you actually take a look at this Hamiltonian, then you can see that the pz orbital contributions to this Hamiltonian are basically not interacting with anything else. And these are actually the pi electrons is exactly as, again, like a chemistry notion that you say, like these are bonds which are formed by molecules which are perpendicular to the bond direction. So if I now focus on the energy band of these pi electrons contributed by the pz, I can take out those 4 matrix elements. Now, there's a couple of the internal parameters which we see if we take a look, for instance, at this Ham C 3.3, and it's given in terms of some sort of parameters, and we can just, give them values for a second. So, for instance, it makes sense to say that the eigenenergy of carbon atom 1 is the same as the eigenenergy of carbon atom 2, and we can set the overall energy scale to 0. It doesn't matter because it only matters like up to which point we want to fill. And then we, for instance, say that the hopping between the 2 electrons should be something like 2.4. Then we get a parametrized Hamiltonian. And now to plot the band structure, we can say that this is a 2-dimensional object. So we want to basically plot the band structure along certain high symmetry path in the 2-dimensional Brillouin zone. So these are the basically high symmetry points, and then the corresponding band structure looks like this. And if you open one of the more recent solid state or condensed matter textbooks, then I'm pretty sure you will find a similar picture like this one. Yeah, maybe just to mention, so this way we can actually, before I stop, we can actually connect to the very beginning where I showed you the mass generation in the fermions, right? So now if you take a look at this crystal structure, Fermi level lies at 0, and you see a linear crossing of energy bands. So if you remember that 1 milli-electron volt is about 10 Kelvin, that means that, like, let's say the scale would be an electron volt. Here it's written arbitrary units. It means that, like, temperature excitations, for instance, take place in a very, very tiny region around this point. So that means around this point, the excitations basically behave as massless mass collective, this collective state basically behaving as a massless fermion. And then one can, for instance, discuss what happens if these fermions interact. Can they, for instance, start to form a mass? Can they break symmetry? Can they induce a gap, for instance, in this graph? I just see, I see that there's a final question, or like there's another question, which says, does this group theory package mean that we can now finally do things that previously were only available in GAP, Sage, and Maple? Or is it much more? How do they compare? To be fair, like, I actually don't know very well the capabilities of Maple, and I briefly, like, let's say I haven't used it myself, but I went into a couple of talks where people were using GAP and developing for GAP. So my very superficial impression would be that GAP is more on the like computational, more focused on the computational algebra side. So it is probably extremely powerful if it comes to calculate, for instance, character tables for very large groups, such as the monsters which were mentioned initially. Where, for instance, people like spend like dedicated time in developing such smart algorithms. I would say that our package is more on the application side. So we really want to focus on basically condensed matter applications, and we want to use the language that is basically used in this community and to make available the tools which are necessary for this community. That's why I don't really see it as competitive. I see it more as a maybe there's a synergy between all of these different tools. All right, with that I would like to thank everybody who joined today's live stream. It was a great pleasure for me to present our package, and I'm looking forward to get, for instance, questions in the future. There's the forum on our webpage, or just send me an email and I'm happy to reply. Thanks.
Thank you, Matthias. Thank you. That was a great presentation. We actually have one more question from someone on Twitch, from FNW65. They're wondering if it carries values for DFT calculations.
Did I understand it correctly? If it carries values? No.
Yes.
Actually, I don't like being aware of what DFT calculations are. I don't fully know what the question is basically aiming at. So I showed this one example, for instance, where we incorporated values from DFT calculations, for instance, for the crystal field theory, for the parameters in the crystal field theory. But in the past, we also experimented a bit in programming basically interfaces to DFT codes, in the sense that you can, for instance, import band structures and get information about the irreducible representation of the states at the bands and so on. But
right. In this case, I think they said they're referring to density functional
theory. No, I know what density functional theory is. It's like density functional theory for electronic structure calculations.
Yep.
So like our package does not contain any density functional theory backbone, let's put it like this. But in some cases there might be ways to communicate with standard density functional theory codes as VARs for quantum espresso or something like this.
All right. Thank you. Are there any other questions from chat that anybody wanted to ask before we let Matthias go? And then, so thank you to everyone for watching. Next week, we're going to have another live stream, which will be kind of a behind the scenes on the Wolfram Technology Conference that took place last week. And it'll be at the same time, 11 a.m. Central next Wednesday. So make sure you come check us out. Oh, just another question from Maudi on YouTube. Can this package work with the Lie groups?
No, not in the sense like this package mainly works on the discrete groups. I showed a couple of examples where we calculated characters for certain elements in SU2 or O3, which are Lie groups, right? But then it's really like characters for the very specific symmetry elements, which, for instance, emerge in certain crystallographic point groups. But we don't have an actual focus on Lie groups, I would say.
Okay, thank you. Thank you everyone for the questions. And like I said, tune in next week, Wednesday, at 11 for another live stream. And if you have any suggestions, you can leave them in our community post, which I think is being posted in the chat as we speak. So thank you everyone. Have a great day. Bye.